Okay, this is MA 255, and let's look at a problem from section 12.2 in the 7th edition, number 37. We have a clothesline that is tied between two poles, and we're told that the poles are 8 meters apart from each other. And when nothing is on the clothesline is taut. Then what's happening is right in the middle, so 4 meters and 4 meters on each side, a wet t-shirt is being hung, and the clothesline then bows, and it bows 8 centimeters. And we're asked to find what is the tension on the clothesline. So the first thing I'm going to do is draw a diagram. And one thing to remember is this is centimeters, this is meters. So we have to decide, do we convert to meters or do we convert to centimeters? Well, I'm going to convert to meters. And so this is 0.08 centimeters. Now I realize that I'm drawing this out of a weird proportion, but I'm doing that so I can fit everything inside the triangle that I'm going to draw here. Because obviously 0.08 centimeters or 0.08 meters is much smaller than 4 meters, but I'm drawing it out of proportion to make it easier to put everything I want to put in. So this is an angle, and this is an angle of these triangles. And this angle I'm going to call theta, but the opposite side of it is 0.08, and the adjacent side of it is 4. Well, this angle over here is also theta. Why? Well, because the opposite side of it is 0.08 and the adjacent is 4. So those are actually the same angles. And then I'm going to label here in the middle as the origin, the center of my universe. And I'm going to do that because from that center of the universe, I'm going to calculate tensions. And this is T1. And this is T. I'm going to actually make this one T1 and make this one T2. It doesn't matter. You could choose to make them in the other order if you wanted to, but I guess I decided to do it this way. And each of these vectors, T1 and T2, have a component in the I direction and a component in the J direction. And one thing to be careful of is when we're talking about this side of our universe, when we're talking about this way up, we're positive in our universe, positive in our universe, positive in our universe, once again negative in the I direction in our universe. One other thing that we know is this angle down here is also theta. And that's from Euclid's parallel postulate. I know that the cosine of theta is equal to the adjacent over the hypotenuse. And in this case, if this is theta, then the adjacent is I. And the hypotenuse is the length of T2. So T2, take its length, multiplied by the cosine of theta, is equal to the I direction component of a vector. With a similar argument, I could do the same with sine, but in the J direction. Same idea. Well, as it turns out, we know what theta is. Theta is equal to the arctangent opposite over adjacent. So that's the arctangent of opposite, which is 0.08, over adjacent, which is 4. So that means theta is approximately equal to 1.15 degrees. Okay, so I know that T1 vector is equal to the something times the I component plus something times the J component. Well, it's the length of T1 times the cosine of theta, which is 1.15 degrees, and that's in the I direction, plus the length of T1 times the sine of 1.15 degrees, and that's in the J direction. Now we also have to be careful because of how we set up our vector for T1. This is T1. In our universe, we set up I and T1's component of I to be negative because here's the origin and we're going left of the origin. So I need to make this negative. Now that represents T1 in both its I and J components. And in a similar fashion, T2 is equal to the length of T2 times the cosine of 1.15 degrees in the I direction, plus the length of T2 times the sine of 1.15 degrees in the J direction. And again, both of those are positive because here's my origin. In my universe, the I component for T2 is on the positive side. I also know from the information that when I add the two vectors together, T1 plus T2, that it's equal to 0.8 kilograms of a wet t-shirt times 9.8 meters per second squared of gravity. And one thing I want to mention here is this is positive, and the reason it's positive is because this is working with gravity, right? How we have our problem set up is gravity is pushing things down, right? So this is positive, which means it's working with gravity. If it was negative, that would mean we're shooting it up, or it's springing up, and it's working against gravity. And we're just doing that based on how I have my problem set up. Okay, so let's solve this thing. So how do we solve it? Well, we're adding T1 and T2 together. So since we're adding T1 and T2 together, let's put the components together. So first the I part. So minus the length of T1 plus the length of T2, and that's the cosine of 1.15, and that's in the I direction, plus the length of T1 plus the length of T2 times the sine of 1.15, and that's in the J direction, and that's equal to 0 times I plus 7.84 times J. So that means that minus the length of T1 plus the length of T2 times the cosine of 1.15 is equal to 0. And I'm getting that because this is the component of I, this is a component of I, they're equal, so that must be true. Well, that means that T1, its length, is the same as T2, its length. That's what that means. I also know from my equation up above that the length of T1 plus the length of T2 times the sine of 1.15 is equal to 7.84. And since that's the case, T1 and T2 are the same, so that's really the same as saying 2 times T1, take its length, times the sine of 1.15 is equal to 7.84. And when we solve for the length of T1, we get 7.84 divided by 2 divided by the sine of 1.15, we get 1.96, or 196. So the length of T1 is approximately 196, so that means the length of T2 is approximately 196. So now all we need to do to calculate our answer is go back up here and look at what T1 and T2 were, we were told they were, plug in our values, and we'll have T1 and T2. Okay, so let's do that. So T1 is equal to negative 196. So the negative times the length of T1 times the cosine of 1.15, and then positive 196, the length of T1, times the sine of 1.15, and that's I and J. And then T2 is equal to 196 times cosine of 1.15, and 196 times the sine of 1.15. And I've just chosen to write it in this vector format instead of the IJK format. And when I do that, I get T1 is equal to, so negative 196 times the cosine of 1.15 is negative 196. And that's in the I direction. And 196 times the sine of 1.15 is 3.92-ish. And that's in the J direction. And then T2 will be exactly the same, but without the negative out front in the J direction. Okay, I hope this video helps you solve